So, friends, welcome again to the class of geomorphology, and in this class we are going to discuss about mass wasting. So, before moving to mass wasting, we must properly understand what does it mean, what is mass wasting, and the meaning it is hidden within this terminology, mass and wasting. Wasting means losing, detaching something, and mass means here we talk about the rock mass. The rock mass we are losing from this original position, that is mass wasting. So, mass wasting is a bridge between weathering and erosion. In weathering, we create some weathered material, and that weathered material has to be removed from their origin and is transported away from this in situ place. So, this process it is called mass wasting. So, during erosional process we have wind action, we have river action, we have glacial action like this, but once we say it is mass wasting, here those agents play negligible role or lesser role as compared to a agent which is called gravity. So, that means in mass wasting case mostly gravity plays major role as compared to other agents. So, that means we can summarize it here. By action of gravity, a mass of rock or a rock mass detaching from the man body and it is sliding down under the force of gravity is called mass wasting, is not it? So, before going to study the mass wasting, we should first know what is this different terminologies and what is the different preconditions which are responsible for mass wasting. Though understanding the precondition is much important in terms of understanding the mass wasting. So, here mass wasting is the collective term used to define all gravitational downslope movement of weathered rock debris. Gravitational, that means gravity plays major role. Downslope, it is the downslope movement, because gravity always stands to tend to pull this system downward. In this weathering and erosional system, if you compare, there is the only wind erosion, mass can move against gravity. Wind can blow material to the uphill. All other weathering agents, they remove the material to downhill, to downslope, but wind is the only parameter or wind is the only agent that can move the mass uphill against gravity. So, that means here gravitational downslope movement of weathered rock material. Weathered rock material means, that means the rock must have to be weathered. So, now the question arises, if it is weathered, to what is the degree of weathering is required? So, the degree of weathering, if we consider, it may be less degree and may be higher degree. Even if the fresh rock, if there are joint planes are there, and through the joint planes there will be movement, and due to this gravitational pulling, a block of rock, a block of fresh rock can be also be removed from the rock mass intact. So, that is also mass wasting. So, the degree of weathering, once we consider, more degree of weathering, more the mass wasting, and reverse is also true. But it is not always true, because we have examples that fresh rock mass, they can be also detached along these joint planes. Weathering, then it is a necessary precondition for movement of rock fragments downslope for the development of the slope. So, here the development of the slope is important. So, development of the slope means, here once we remove the material, we are removing the material, that means we are creating slope, we are changing the slopes. So, slope changes takes place due to mass wasting. Sometimes the slope may become gentler, due to removal of mass. Sometimes this gentle slope will be steeper due to removal of mass. So, it is constantly modifying the slope, hill slope, river slope, any type of slope, it is constantly modifying. So, the mass wasting is plays important role in modifying the hill slopes. So, that is why it is called mass wasting and hill slope evolution. So, whenever a particle is moving, that is gravity adds to downslope component of this motion produced by other forces. That is, other forces means, suppose it is a sloping surface, on the sloping surface a particle or a mass of rock, it is moving downward. So, once it is moving downward, other forces also accelerating the movement or influencing the movement. What are the other forces? One is the slope itself. Larger the slope, the rate of movement will be more. Similarly, mass of the material, it is a small particle, it can stable here, or in the higher slope or the steeper slope, even a small particle can be stable. But the same particle, it is in lower slope, it is not stable. That means, it is in a further higher slope, it will fall down. A mass of particular mass, it may stable here in this slope, if it is lower slope, it is stable, but here it is relatively stable, but here it is unstable. So, slope is playing another role here. Then water, if water is there, so water in which form it is, that also depends upon. If water is flowing, that means it is increasing seepage pressure. So, material will be easily removed from the slopes. So, that means except gravity, some other factors do work together with the gravity to change the hill slope from time and space. So, this definition implies gravity is the sole important parameters which play major role for transportation of material rather than wind, water, ice and molten lava itself. So, whenever we talk about this term mass wasting, we always keep in our mind that gravity here plays important role or major role as compared to other parameters. So, flowing water is excluded here definition, but water nevertheless plays an important role in mass wasting. How? Water has three types of role. First is, it is oversteepening of slopes through surface erosion at their bases. For example, we have a sloping surface and at the slope, at the base of the slope, a river is flowing. For example, in this figure, here is a sloping surface and a river is flowing. So, once the river is flowing, it is cutting its base, the toe of the slope, here it is cutting. So, once it is cutting the toe, so that means this part of the slope became unstable. So, river has direct effect on the slope and stability. Second thing is that by adding weight to the rock mass, it might exceed the threshold of failure. So, once it is a sloping surface, for example, the second figure here if you can find, it is a sloping surface and the rocks are highly weathered. So, during raining what happens, this weathered material they absorbs water. So, its mass increases. So, once the mass of a sloping surface increases, it adds, it promotes mass wasting, it promotes its removal because its own weight increase. So, once its own weight increases, the mass will easily pull down. So, that is why by increasing or by adding weight of the rock mass, that might exceed the threshold failure. Then third point is by generating seepage pressure through downward flow, groundwater flow. By seepage pressure, once the water is flowing within the medium, it is seepage pressure is increasing. So, seepage pressure, it behaves as a buoyant system. So, that means it will remove the material, easily create cracks. So, easily create cracks, that means there is possibility that this cracked portion or this detached portion, they can easily detached from this main body. So, water has three types of role play in this mass wasting in addition to gravity. Water has a complex effect on the sliding friction between surface of the rock forming mineral. Some minerals the sliding friction increases with the presence of water, and for some mineral the sliding friction decreases. For example, if we confine ourselves quartz, feldspar, calcite, in the presence of water the sliding friction among these different mineral that increases. That means the rock become more stable. The minerals they are bounded with each other due to the sliding friction. However, some other minerals like the clays minerals, the sheet structures, if water remains there within their surfaces, it behaves as a lubricant. So, once it behaves as a lubricant, there is chance of failure increases. So, that is why water has dual effect. For some minerals it is increasing the friction, and for some certain minerals it is decreasing the friction. So, it is very important the seepage pressure generated by groundwater flow that have such great influence on slope stability and mass wasting. Okay. So, seepage pressure plays an important role. The more the seepage pressure is, the easy for the system to pull down, easy for the rock mass to pull down the gravity. So, before going to study the mass wasting, its effect, its mechanism, its agents which are responsible and the type of mass wasting, we must understand certain basic parameters, basic understanding what is science behind it, why the mass wasting takes place. So, first parameter is the angle of friction. So, angle of friction, that is otherwise called the angle of repose. So, a series of simple experiments has been carried out to understand what is the angle of repose and how this angle of repose is defined or it changes with the material property. For example, if we allow free fall of sand particles through a cone, through a funnel, it will create a cone, and this angle of repose, if you see here, it is around 30 to 35 degree. But this 30 to 35 degree, it is not same as the material changes, the angle of repose changes. For example, if you see here, for fine sand it is about 35 degree, for coarse sand it is about 40 degree, for gravels it is 45 degree, for dry sand, drier coarse sand it is more than that, and it is most sand it is about 90 degree or so, and if it is water saturated sand it is like that. So, that means I want to say, depending upon the property of the material, depending upon the water saturation, the angle of repose varies. The tangent to the angle of repose of dry granular material is slightly greater than, but approximately equal to the coefficient of sliding friction of this material of the mass friction, that is the angle that is called phi. So, here the material changes, the angle of repose changes, the water content changes, this is angle of repose changes. That means, if we apply this knowledge in hill slope composed of fine material will be different degree of sliding, different degree of repose or different angle required for failure. Similarly, the hill slope composed of gravels, that will fail at a different angle. It is saturated, it is fail at different angle. Water seepage is going on, it will fail at different angle. So, that means, by those simple experiments in the laboratory, we can apply those knowledge in natural environment to understand this, understand the basic properties of this mass movement or a particular topography or particular angle of the slope and particular material involved. The same thing here, the fine sand 35 degree, coarse sand 40 degree, angular pebbles like 45 degree, and if it is subangular or rounded pebble, it is less than 45 degree. So, that means, the texture, this material, the size, that defines the angle of repose. The balance of force between gravity and friction determines the stability, because once a block is placed on a sloping surface, there will be angle of friction, there will be friction between the surface and the material. gravity always wants to pull it down, and the frictional force it try to make it intact with the slope. So, it is the tussle between the gravitational pull and the frictional force. So, whichever is more that will affect, and that is totally governed by the type of material and the angle of the slope angle. If its slope angle is less, here frictional force will dominate and gravity will fall here. But it is the angle of repose or the angle of slope is more, here gravity will play major role as compared to the frictional force and the block will move down. So, the coefficient of sliding friction of a particle is equal to the ratio between the downslope component of weight and the component of weight acting perpendicular to the slope, then the particle is moving. So, this tussle between the two that define whether this particle will move downward or it will remain as it is at the surface of intact. If the same sand is deposited in a saturated condition under water, the angle of repose of the cone will be virtually identical of this angle of repose at the dry condition, provided that the water seepage is not there. But once the water seepage starts and the water, suppose we pour water at the tip of this cone and is allow it to flow at the base. So, once the water flow at the base of this cone, the water or the sand starts falling. So, the failure occur at the sand cone once the water is percolating down, because due to the seepage pressure. But water is poured gently on the top of this cone in the dry sand and allow to seep downward and outward. So, failure occurs as soon as the water reaches at the slope face. Flow of rainwater runoff in the surface soil of the slope reduces the stable angle of repose of the soil to less than half of the dry angle. It is very sensitive to understand here. That means, once we have a system, we have a slope surface, weathered surface, or it is composed of sand or any material which can absorb water. Until unless water getting seepage through that, water is flowing out of the system. So, that means up to that may be some stability will be there. Once water seepage starts at the base, that means seepage pressure it increases. So, seepage pressure increases, that means this part of this material, part of the slope will be slide down. So, seepage pressure in addition to gravity also plays important role for defining the stability of the slope. So, another point to understand here is the cohesion. Is the fine grained sediment, exceptionally clay sized particles have strong cohesive surface force between them, determine the electrostatic charges of grain structure that immobilize the water film between them. So, here due to the cohesion, the particles they remain intact with each other. So, seepage pressure is not here, seepage pressure because water is not flowing here. Then the cohesive force act in addition to the mass friction to determine the angle at which the slope failure occur. That is why in clay surfaces we can cut it vertically, but it will remain stable. Why? Due to the cohesive forces. But the non cohesive system like the sand, if we cut it in vertical faces, that can removed, that there will be sliding. So, that is also another field ways to understand the silt deposit and this sand deposit. In loess that is wind blown dust particle, mostly silt and clay. If you cut it vertically, the vertical surface will remain there for considerable time. But the sand surface, if you cut it vertically, it will not remain vertical for a considerable or for the same time, because there will be sliding of sand due to the non cohesive nature. But these clays, the silts, they have cohesive forces between them. So, they remain it intact. That is the field way, or the field device or the field phenomena, how you can distinguish whether you are dealing with a sand deposit, you are dealing with a silt deposit. So, pore water, when we talk about the water seepage or water absorption of a system, this pore water can either add or subtract from mass strength. For example, suppose the voids of the mass are only partially filled. For example, this figure you see the voids are partially filled. So, once it is partially filled, the capillary surface tension of this water film that will draw the mineral grains close to each other. So, the pore pressure is described negative because inward it is intacting, it is binding these particles with each other. So, here the pore pressure is negative. So, which means once the pore pressure is negative, it is adding to the frictional force. So, making the grains stable, but in the latter case if it is totally filled, when the void space is fully saturated, however, cohesion is lost because there is no surface tension and part of this overburden weight is transferred to the water from the individual grains. Pore pressure is then positive and has a buoyancy effect, reducing the strength of the mass, then the failure occurs. So, if the system is half filled, the system is partially filled, that will be more stable as compared to the system which is total filled with water. Whenever a mass from the slope will fall or not, that will explained by this equation. What is S is equal to C plus sigma tan phi, where S is the shear strength, C is the cohesion, sigma is the stress component perpendicular to the surface, phi is the mass angle of friction. This equation which relates the shear strength of solid mass just at the threshold of failure and stress applied on it. It is now known as Mohr's-Coulomb failure cohesion criterion. So, this Mohr's-Coulomb failure criterion that defines whether a particular mass, a particular block of rock that will remain stable on a sloping surface or it will fall down. In cohesionless sand and larger gravels, this cohesion is 0. So, C equal to 0 and mud and clay, C is maximum or it is a significant role and hence cohesion increases shear strength. Many moist clays hold vertical faces of modest height without failure, which non-cohesive material can never do. So, that is the reason silt surface can be or clay surface can be cut vertically and they remain vertical for a considerable time. However, the sand surface cannot. Here two figures are given or these two photographs. One here you see the sand, it is cutting into vertical surface, but failure is there. But silt and clay, this relatively become stable due to this cohesive forces between them. So, an equivalent form of Mohr's-Coulomb failure criterion takes into account the excess pressure of pore fluid. So, whenever we are talking something few minutes back we are talking Mohr's-Coulomb's failure criterion, we are talking something about the dry system. But suppose we introduce the seepage pressure in this pore fluid pressure within the system, including the seepage pressure. This concept is called principle of effective stress. Here S equal to C dash plus sigma dash plus tan phi dash. C dash is the effective stress of cohesion, sigma dash sigma minus u effective stress component normal to the surface as reduced by positive fluid pressure u. Positive fluid pressure means fluid pressure is outward, that means it is totally filled, the system is totally filled. If it system is not totally filled, that the fluid pressure is negative and positive fluid pressure means it is outward, the pressure is outward. Sigma dash it is the effective stress angle of friction. So, these two equations, one is for the filled system, water filled system, another for the dry system, that indicates or they define whether a slope will fall or will remain intact. In silt and clay rich sediments, the water content becomes a major parameter for deformational behavior. Water content is usually assessed as a percentage, the ratio of weight of water in sample divided by the weight of the dry sample. Mixture of various size fractions behave differently as compared to the individual abundance. It is also very important to understand here. if we have a mixture of sand, silt, clay, it will or gravel. So, the system will behave differently because different particle size behave differently. Rather than we have a particle size of a rock particle size in a rock which is uniform, that will show uniform behavior, but a rock composed of different type of particles, different size of particles, that will behave differently. So, in a slope failure we have to understand what is the angle, what is the degree of saturation, what type of material it is composed of. So, all those things should be taken combinedly to define whether the slope will going to fail or it will be remain stable. Some clay minerals can absorb water equal to several 100% of their dry weight. So, here some clay minerals are given. Those clay minerals, now you can say here it can absorb water, here the water compared to this dry clay, here dry clay mineral and here wet clay mineral water molecules. There are some clay minerals they can absorb water some hundreds of times of their own weight. So, we have to define, we have to know what type of clay is there, what type of clay is present in the slope material. So, that is why before going to any major construction, so we must analyze the rock material, whether it is composed of that type of clay which can absorb, we can swell, we can hydrate and dehydrate seasonally. So, that has to be removed, that place, their sites should be avoided, because these are the potential site for future failure. Then another point is called liquid limit, plastic limit and plasticity index. So, liquid limit is based on the rate at which the standard conical weight sinks into a paste of water and sediment. It defines the water content at which the sediment pass from plastic to a liquid state. Here a graph is given, this increasing moisture content and increasing soil volume. So, here if you see, this is liquid limit. Liquid limit means it is a plastic, this side is plastic, this side is liquid or viscous liquid. So, it is the amount of water which is absorbed by a soil or absorbed by the material by which that behaves like liquid, that is the liquid limit. The liquid limit, it is good measure of cohesion between the liquid limit, cohesion essentially 0. So, once we are reaching at this liquid limit, that means the system try to flow, the system starts flowing. So, that means here cohesion is 0. So, before liquid limit, this some cohesion is there, some cohesive force is there, but once it reaches, that means a material if it absorbs particular amount of water, the cohesion decreases, cohesion becomes 0 at the liquid limit. Clay rich soil typically have liquid limit ranges from 40 to 60%. So, that means we have a clay in a slope, the clay can absorb water 40 to 60%. So, beyond that will start flowing. Similarly, plastic limit is also another measure of water content defined by the water content at which the mass from solid to plastic state. So, it is defined by the water content at which sample can be rolled into a 3 millimeter diameter like soda straw rod without crumbling. So, here if in figure if you see, this is the clay content or this water content in the clay or the soil which is rolled like a rod. If the rod remains intact without breaking, that means it is within the plastic limit. If it is breaking, that means the plastic limit crosses. And generally the liquid limit and plastic limit, it is dependent upon the clay content of a rock of the soil. It is a good measure of clay content of the sample, because silty or sandy soils with little clay content cannot be rolled into such type of rods. So, the number of the percentage of clay increases, this plastic limit also increases. So, more the clay is there, it can be, this rock can be created thin rod less than 3 millimeter also without breaking. So, the plasticity index is the numerical difference between the liquid limit and plastic limit. If it is low, suppose it is 5%, the sediment will change readily from a plastic semi-solid to a liquid. A plasticity index of 20% or more implies that the mineral can accept much water before it loses its shear strength. So, that means here we can define the plastic limit of the slope material. If this plastic limit is more, that means the chances of failure will be less. So, that is why the plastic limit, liquid limit and this plasticity index that define whether this slope is going to fail for a particular amount of water or not. Now, the rates of downslope movement. The rate of downslope movement, it is depending upon the slope. If it is slope is more, the rate of movement will be more. If slope is less, the rate of movement will be less. So, here the shear strength acting parallel to the slope, which causes a particle to move down slope, is proportional to the sine of the slope angle. So, here the slope is less, suppose therefore, the line is moving like this. So, the rate of movement of this block will be less. Here it is given here, it is 0 degree, then 30 degree, then 60 degree, then 90 degree. So, once the sine of this angle increases, so that means the rate of movement of a block also increases. So, at what speed this slide will occur, at what rate the slide will occur, at what rate or at what speed the slope failure will occur, at what is the speed of this intact mass will come down, either it is slow movement or it is a rapid movement, that depends upon the slope angle. So, the rate of downslope movement of small loose rock fragments responding to stress would also be proportional to the sine of the slope angle. Downslope movement is the slowest on the gentle slope and increasing rapidly with increasing upslope. Slope angle on vegetated non-cohesive weathered debris such as loose rock rubbles are virtually between 25 degree to 40 degree, somewhat less than the measure of calculated angle of repose of the debris. So, that means debris if it is there, it will fail fast as compared to other materials. So, natural slopes steeper than 40 degree are usually nearby barren rock debris, and it is in British terminology it is called cliff. So, these are called cliff surface, that means it is a steep slope angle totally devoid of any debris, because any debris created here it will fall down directly, because here slope angle is more. So, slope angle more, rate of movement is more. So, that is why any material which is removed from here can easily fall down here, that is why these cliff surface are devoid of any rubble material or loose material. On vertical slopes, a loosened rock particle drop under the free acceleration of gravity, the rate of fall limited only by the air resistance. Here if you see in this photograph, this material is falling down freely, only the air resistance is there, nothing, this is called free fall. So, these are these terminologies has to be understood properly before moving to study this mass wasting and its classification, and why mass wasting is important to understand before going for a developmental project, before going to slope stability projects etc. So, I think it is for today, and we will meet in the next class. Thank you.